Good afternoon, everyone. So, we will be carrying forward of whatever the problem we have left in the earlier class. We are looking into the solution of non-homogeneous partial differential equation using Green's function method. Now, we are looking into an elliptical partial differential equation, and we came up to a solution almost at the last step. Only few steps are left, and we will be solving those that problem first completely, then we will move forward to other problems. Okay. So, solution of non-homogeneous elliptic PDE. So, we considered a problem something like this: del square u del x square plus del square u del y square is equal to delta x is equal to some function of x and y. At x is equal to 0, we had u is equal to u 0 1. At x is equal to 1, we had u is equal to u 0 2. At y is equal to 0, we had u is equal to u 0 3. At y is equal to 1, we had u is equal to u 0 4. So, we had this equation. So there were 5 sources of non-homogeneity. We first constructed the causal Green's function. We evaluated the causal Green's function using complete eigenfunction expansion method, and then we looked into we evaluated the eigenvalues and eigenfunctions. We had 2 independent eigenvalue problem in this whole problem equation, that was in x direction as well as in y direction. Now, what we did, we proved later on that Laplacian operator, that grad square operator, is a self adjoint operator. So, therefore, Green's and since all the boundary conditions are homogeneous, the adjoint Green's functions must be having the homogeneous boundary condition in order to have the bilinear concomitant term to vanish. So, therefore, the operator is a self adjoint operator, and we have a self adjoint system in this particular case. The operator is self adjoint, the boundary operator is also self adjoint. So, we had a completely self adjoint problem. So, we need not to go for an expression of G star, and we need not to connect G star with U, since G is equal to G star, because L is equal to L star. So, therefore, we can directly hook up the actual equation, governing equation U, with that of governing equation of G. We really did that, and finally came to a point where we had the solution in this form. The solution becomes U x naught y naught is equal to f 0 to 1 y is equal to 0 to 1 g dx dy. That was the that was the boundary condition, and then we had the other terms. So, these are the this term comes because of the non-homogeneous term in the governing equation, minus u 1 0 y is equal to 0 to 1 del g del x at x is equal to 0 dy and then we had one more term u 2 0 integral y is equal to 0 to 1 del g del x at x is equal to 1 dy. Then we had 2 more terms corresponding to the 2 non-homogeneities in the y boundary, u 3 0 integral 0 to 1 over x del g del y at y is equal to 0 times dx, non-homogeneous boundary condition at x is equal to at y is equal to 0. Then u 4 0 0 to 1 over x, this will be del g del y at y is equal to 1 times dx. So, there are 5 sources of non-homogeneities in this problem. The first one comes because of the non-homogeneity in the governing equation. The second, all these 4 terms appear because of the non-homogeneity in the boundary conditions. Therefore, the first term is basically a double integral time. It is a volumetric integration time because it is applicable throughout the whole volume. Rest of the 4 terms are basically the surface integral time. They represent the boundary conditions because of the non-homogeneities in the existing on the boundary. So, let us solve this problem completely. Now, we look into the function of g, the expression of g x y x naught y naught. So, if you look into the expression of g, this will be 4 summation over m equal to 1 to n summation n is equal to 1 to infinity. So, it will be sin n pi x naught sin m pi y naught sin n pi x sin m pi y divided by m square plus n square pi square. So, that is the Green's function. Now, we look into this integrals, 5 integrals one after another. So, the first integral is quite complicated. F is coming out. So, it will be 0 to 1 g dx dy. So, m square plus n square pi square. We keep the summation outside and this will be sin minus 4 sin n pi x naught sin m pi y naught sin n pi x sin m pi y dx dy. So, therefore, f summation over m summation over n minus 4 sin n pi x naught sin m pi y naught m square plus n square pi square integral sin n pi x dx integral sin m pi y dy from 0 to 1 from 0 to 1 will be minus 4 f summation over m summation over n 1 to infinity sin n pi x naught sin m pi y naught. So, they will be treated as constant because the integration over x and y. So, this will be we already solved this one earlier. So, this will be cos 1 minus cos n pi over n pi 1 minus cosine m pi divided by m pi, and in the denominator you have m square plus n square pi square. So, that is the complete solution of the first part. Let us write it down into more amenable form. So, this will be 1 minus cosine n pi 1 minus cosine m pi m n m square plus n square pi to the power 4 sin n pi x naught sin m pi y naught. So, that is I1. Next, we solve for I2. I2 is minus u10 y equal to 0 to 1 del g del x evaluated at x equal to 0 dy. So, what is del g del x? Del g del x is nothing but minus 4 summation over m summation over n sin n pi x naught sin m pi y naught del g del x. So, it will be n pi cosine n pi x sin m pi y divided by m square plus n square pi square. So, this will be minus 4 summation over m summation over n pi divided by m square plus n square pi square sin n pi x naught sin m pi y naught cosine n pi x sin m pi y. So, integral of this I 2 will be minus u 1 0 minus minus plus multiplied by 4 double summation 1 over m another over n. So, if we integrate this out with respect to y. So, if we integrate it out with respect to y, so it will be simply integral of sin m pi y dy. So, and del g del x evaluated at x is equal to 0. So, let me write it down. So, one more step m square plus n square pi square sin n pi x naught sin m pi y naught cosine n pi at x is equal to 0 cos 0 will be 1. So, this will be integral of sin m pi y dy from 0 to 1. So, this will be 4 u 1 0 summation over m summation over n n pi m square plus n square pi square 1 minus cosine m pi divided by m pi sin n pi x naught sin m pi y naught. So, 1 pi will be cancelling out. So, it will be n into cosine m pi divided by m into m square plus n square pi square sin n pi x naught sin m pi y naught. Similarly, we can evaluate the next integral I 3. The I 3 will be del g del x evaluated at x is equal to 1. So, it will be u 2 0 4 u 2 0 double summation 1 over m another over n. So, it will be 1 over and it will be evaluated at x is equal to 1. So, it will be cosine n pi. So, cosine n pi divided by multiplied by n pi. Okay. So, this is divided by m square plus n square pi square sin n pi x naught sin m pi y naught and then integral 0 to 1 sin m pi y dy. M pi y dy. So, therefore, this will be having value u to 0 m and n pi cosine n pi divided by m square plus n square pi square 1 minus cosine m pi divided by m pi sin n pi x naught sin m pi y naught. So, that is the value expression of I 3 and you will be getting I 4 okay. So, that will be okay. So, I 1 I 2 I 3 I 4 and I 5. So, it will be minus u 3 naught. So, minus plus 4 u 3 naught m n then m square 1 over sin m pi x naught sin m pi y naught divided by m square plus n square multiplied by pi square. Then it is integral of del g del y evaluated at y is equal to 0 dx. So, del g del y we just multiply del g del y will be nothing but m pi cosine m pi y naught evaluated at 0. So, that will be 1. cos 0 will be 1, and then we will be having integral 0 to 1 sin n pi x dx. So, 4 u 3 0 summation m summation n sin, okay, this will be m pi, then 1 minus cosine n pi divided by m square plus n square pi square into n pi. So, pi will be cancelled out, it will be sin m pi x naught sin m pi y naught. And similarly, we will be having I 5. So, I 5 will be, I guess it will be minus 4 u 4 naught summation over m summation over n, and we will be having m pi cosine m pi divided by m square plus n square pi square divided by multiplied by n pi in the denominator. So, it will be 1 minus cosine n pi 1 minus cosine m pi n pi multiplied by sin n pi x naught sin m pi y naught. So, therefore, we can add all these contributions up and we will be getting the complete solution. So, complete solution will be obtained u as a function of x naught y naught will be simply sum up all the solutions I 1, I 2, I 3 and I 4. Okay. Now, if that is the case, you will be finding that the right hand side you will be having only summation of some term constant term multiplied by summation of some variable multiplied by sin m pi x naught sin n pi sin m pi y naught sin n pi x naught. So, therefore, we can change the variable from x naught y naught to normal variable x and y. So, we will be getting u as a function of x and y. So, we will be getting the complete solution of elliptic partial differential equation using the full eigenfunction expansion method by using Green's function procedure. Now, one more thing I would just like to talk here, that if the boundary conditions are different, if instead of boundary if instead of Dirichlet boundary condition for the same problem, 2-dimensional problem, grad square u is equal to 0 is equal to f, if you have that at x is equal to 0, instead of u, del u del x will be equal to 0 and u is equal to 0 and y is equal to 0 and x equal to 0, del u del x is 0 and u equal to 0 at x is equal to 1 and y is equal to 0, at y is equal to 0, u is equal to let us say q 1, okay, and this is this let us say q 2, this is q 3, and at y is equal to 1 you have u is equal to q 4, then corresponding Green's function will be the corresponding Green's function can be written as grad square g x y x naught y naught is equal to delta x minus x naught delta y minus y naught. So, at x is equal to 0, we should have del g del x is equal to 0, at x is equal to 1 we should have g is equal to 0, at y is equal to 0 we should have g is equal to 0, and at y is equal to 1 we should have g is equal to 0. So, therefore, the eigen functions in this case will be the cosine functions cos n pi x, and eigen functions in this case in the y direction will be sin m pi y. So, therefore, Green's function here becomes minus 4 summation over m summation over n sin n m pi y naught cosine n pi x naught sin m pi y cosine n pi x divided by lambda, and lambda will be in this case is n square pi square plus 2n minus 1 by 2 square pi square. So, in this case the eigenfunctions will be constituted by the cosine functions, and in x direction, because you have a Neumann boundary condition in the x direction, and eigen functions will be constituted by a cosine function in the x direction and sine function in the y direction, and this will be this will be cosine function in x. So, this will be m okay, and the eigenvalues will be constituted by m square pi square plus 2n minus 1 by 2 whole square pi square, because these are the eigenvalues in the x direction and these are the eigenvalues in the y direction. If we have the problem like del square u del x square plus del square u del y square is equal to delta x minus x naught delta y minus y naught, and actual problem we have, let us say Dirichlet boundary condition on u is equal to u01, u is equal to u02, this is at x is equal to 0 and this is at x is equal to 1. Then we have this, and then at y is equal to 0 we have, let us say del u del y is equal to 0 and let us say u03 constant wall flux condition, and at y is equal to 1 u is equal to u04. Then we the corresponding Green's function solution will be, governing equation will be del square g del x square plus del square g del y square is equal to, okay, this will be some function of x and y. So, this will be delta x minus x naught delta y minus y naught, that will be, we are replacing the non-homogeneous term in the governing equation by the Dirac delta function, and the boundary conditions on u on g will be at x is equal to 0 and at x is equal to 1 g is equal to 0, and at y is equal to 0 del g del y is equal to 0 and at y is equal to 1 g is equal to 0. Therefore, eigenfunctions in the y direction will be the cosine functions, eigenfunctions in the x direction will be the sine function, and lambda will be given by this will be n pi will be the eigenvalues n square pi square plus 2n minus 1 by 2 m minus 1 by 2 whole square pi square will be the eigenvalues, and the Green's function will be g x y x naught y naught will be nothing but summation 1 over 1 summation over n m another over n minus 4 n square pi square plus 2 m minus 1 by 2 whole square pi square, and in the numerator we will be having cosine functions, cosine m y naught are the eigenfunctions. So, sin n pi x naught cosine m pi y naught sin n pi x cosine m pi y as the Green's function. The rest of the procedure is exactly the same whatever we have done earlier. If you have the Neumann boundary condition on in both x and y, then you will be having the cosine functions as the eigenfunctions. So, if you are talking about a problem like del square u del x square plus del square u del y square is equal to f of x y, and at x is equal to 0 del u del x is equal to u01, at x is equal to 1 u is equal to let us say u02, at x at y is equal to 0 del u del y is equal to u03 and at y is equal to 1 we have u is equal to u04. In that case, the Green's function will be del square g del x square plus del square g del y square is equal to delta x minus x naught delta y minus y naught. So, at x is equal to 0, del g del x is equal to 0, at x is equal to 1, g is equal to 0, at y is equal to 0, del g del y will be equal to 0, at y is equal to 1, g is equal to 0. So, therefore, in this case cosine n pi x and cosine m pi y are the eigen functions with the eigenvalues 2n minus 1 pi by 2 and with the eigenvalues 2m minus 1 pi by 2. So, therefore, g as a function of x y x naught y naught should be minus 4 summation over m summation over n cosine m pi n pi x naught cosine m pi y naught cosine n pi x cosine m pi y divided by 2n minus 1 pi by 2 square of that plus 2m minus 1 pi by 2 square of that, then bracket end. That will be the expression of Green's function, and one will be getting the one will be getting the solution exactly the same way we have done before. And similarly, if one of the boundary conditions are the Robin mixed boundary condition, then you will be getting the transcendental equation as the eigenvalues, and we will be getting the sign functions as the eigenfunctions in the corresponding direction where the Robin mixed boundary condition exists. The other boundary condition, the other direction, the eigenvalue problem can be evaluated as we have done earlier. So, we will be able to get the expression of g. Once we get the expression of g, the rest of the calculation follows exactly the same way as we have done earlier. We connect u with g and completely solve the problem, and in a general case like this there will be 5 sources of non-homogeneity, because in the original problem there are 5 sources of non-homogeneity. Corresponding to each of these term will be getting the 5 terms in the final solution. Out of these 5 terms, one will be the volumetric integral corresponding to the non-homogeneous term appearing in the governing equation. The other 4 will be the surface integral terms to corresponding to the non-homogeneity in the boundary conditions. And the way we have solved the earlier first problem in this class, exactly the same way these problems have to be solved and completed by using the Green's function method. So, we have come to the end of solution of non-homogeneous partial differential equations using Green's function methods. This is the most general form, and we have considered all the boundary conditions to be non-homogeneous, and combinations of all sorts of boundary conditions, Dirichlet, Neumann, both Neumann, Dirichlet, Robin mixed and Robin mixed, Neumann, and all this. So, we have seen how the Green's function will be evaluated by full eigenfunction expansion method, and then it must be hooked up or linked with the original differential equation, and we will be getting the entire solution by the analytically if the problem is linear and non-homogeneous. Okay, we completed that part. Next, we move to the another method of solution, mathematical tool that we are going to use quite often, and several times we use this technique for solution of chemical engineering problems. Many of such problems can exist. I will name some of these. I will first name about the method that we are going to discuss now on. It is the similarity solution method. This method is quite popular when we are solving the boundary layer equations. So, when we are solving the boundary layer equations, this becomes quite important. So, let us first see what these boundary layers. Boundary layers are the locus in a flow field where the velocity components or the values of velocity will be 99% of the bulk velocity. Consider the flow over a flat plate. So, in the free stream, the velocity is u infinity. At the boundary of the plate, the velocity is 0 because of the no slip boundary condition. As you go up, the velocity keeps on increasing, and beyond a particular point it becomes u is equal to u infinity. So, one can identify a locus in the flow field where the every point of this locus will be having a velocity 99% of free stream velocity. That particular locus is called the boundary layer. Now, this boundary layer can be, if we are talking about momentum transfer, we can have a velocity boundary layer. This is also called hydrodynamic boundary layer. Whenever we will be having a heat transfer case, then there will be a profile and there is a mismatch of bulk temperature and the wall temperature. So, there is a profile existing in the flow field where temperature at every point will be 99% temperature of the free stream. So, that boundary layer is called the thermal boundary layer. Whenever there is a concentration field, that there is a mismatch of bulk concentration and the wall concentration we kept in different. So, there is a concentration gradient. So, therefore, there exists a profile in the flow field of the concentration such that at every point on this there exists a locus on where every point there will be concentration which will be equal to the bulk concentration. So, this is known as concentration or mass transfer boundary layer. These boundary layers are typically occurring in the order, the thickness of these boundary layers typically in the order of micron, 10 to the power minus 6 meter, or it might be slightly more, 10 to the power minus 4 meter, but not larger than this. But all these momentum transfer, heat transfer and mass transfer, they are occurring within this thin boundary layer. That is why the boundary layer calculations are quite important in all chemical engineering applications, because heat, mass and momentum are basically getting transported within this thin boundary layer. So, therefore, we do the boundary layer equation. Now, if you look into the profiles of velocity or temperature or concentration within the boundary layer, you will see that first of all there are two characteristics of this boundary layer. The thickness of this boundary layer is increasing as you go along the length. So, therefore, this thickness is here delta 1, at this location here it is delta 2. So, in general delta is a function of x and it is an increasing function of x, but with a decreasing slope. That is number one characteristic. Number two characteristics is that the conditions on edge of the boundary layer everywhere must be satisfying two conditions. One will be that at delta at y is equal to delta at the edge of the boundary layer, at the edge of the boundary layer at y is equal to delta, u may be u free stream and del u del y should be is equal to 0. The y gradient of velocity at the edge of boundary layer must vanish, and similarly at y is equal to delta, t is equal to t infinity and del t del y must be equal to 0. That is for the thermal boundary layer. For concentration or mass transfer boundary layer, c is equal to c infinity del c del y must be equal to 0 at the edge of boundary layer or at y is equal to delta. So, these conditions are compulsory conditions, they are necessary and these are called the boundary layer conditions. Okay. Now, if you look into the profiles of dependent variable as a function of x and y within the boundary layer, the profiles will be, if it is a velocity boundary layer. So, velocity is 0 over here and it is maximum there. So, the profile will be something like this. So, there existing a profile within the boundary layer. This is at the location x where the velocity is 0 and velocity is high there. So, if you plot velocity v x, okay, as a function of y at y is equal to 0, it is having a high value. Okay. At y is equal to 0, it is having a high value, and y is equal to infinity. Okay. So, it is the other way around. At y is equal to 0, this is having a no slip boundary condition. So, this value will be equal to 0, and at y is equal to delta, it will be having a value. Okay. Let us say this is v infinity. Similarly, when this is for a particular x location. Now, if you look into another x location, the velocity profile will be something like this. So, it will be 0, then it increases and going up to value y is equal v x is equal to infinity. So, this will be at a particular location x 1, then you will be having another profile of v x. This is a particular location x 2. So, these will be another location x 3, this will be another location x 4. So, therefore, these profiles, the nature of these profiles are similar in nature. These profiles are similar in nature and they are known as self-similar profiles. Known as self-similar profiles. Now, if you plot the value of velocity, let us say, as a function of y, you will be having the free stream velocity, okay, at a particular level. This is v infinity, that is the free stream velocity, and it reaches infinity at different values of delta. So, delta keeps on increasing. So, as okay. So, this is a particular x location, this is another x location, this is another x location, this will be another x location. Okay. So, there may be another profile here. So, this is x naught. So, as x increases, so the velocity will be attaining the free stream velocity at different values of y. So, this is corresponding to delta 0, this is corresponding to delta 1, this is corresponding to delta 2, this is corresponding to delta 3, and this will be corresponding to delta 4. Now, if I plot delta as a function of x, the plot looks something like this. So, this is the boundary layer profile. Okay. So, therefore, we will be getting the velocity profile as a function of y for different x location, and if you just look into this curve, that all these profiles are self similar, they are similar profile. Now, if we now plot, if we normalize this variable, the y with respect to delta which is nothing but a function of x. Okay. So, that means if you plot V x as a function of y by delta, where delta is eventually function of x, let us see what we get, what is the nature of this plot looks like, how this plot looks like. If we express y as y by delta, which is nothing but a function of x, then if we plot V s as a function as this quantity y by delta, that means we are normalizing this axis by the corresponding deltas. So, this is delta 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 delta, where each delta is a function of x. Then what we will have, we then, since we are now not differentiating the values of x 0, x 0, x 1, x 2, x 3, x 4. We are not differentiating with respect to at what location we are talking about, because we are now normalizing, we are plotting V x as a function of y by delta, which is in fact a function of delta. So, in this quantity, if we plot velocity as a function of y by delta, we are not at all differentiating at what x location we are talking about. Since the curves are similar, then what we can expect out of this, if we really do that, then all these curves will be superposing on each other, they will collapse on a single curve. Why they will collapse on a single curve? Because we are now dividing it at y is equal to delta. So, we are normalizing against the delta, which is eventually a function of x. So, this curve and all these curves will superimpose on this on one another, and we will be getting a single curve. So, in this case, we will be getting a single curve . So, by doing a so therefore, all these curves will collapse. Curves correspond to various x collapse on a single curve. So, therefore, what it means is that initially we had V x as a function of x and y, and now what we can do is that we can. So, therefore, they will be having separate curves as a function of when we plot V x versus y as a as different positions of x. Now, since we are getting a single curve V x as a function of y by delta, we call this a parameter, new parameter eta. So, we will be getting V x as a sole function of eta, because the whole characteristic can be represented as a single curve. Okay. So, what this means? This means that here we are talking about two variables, two independent variables, and therefore, and in this case we have one independent variable. Now, whenever we will be having two independent variables, the governing equation is partial differential equation. When we will have only one independent variable, the governing equation is ordinary differential equation. So, therefore, by and this parameter eta, which is a combined parameter of y and x, delta is essentially function of x. So, it is a combined parameter of y and x, is known as a combined parameter or similarity parameter. Okay. So, once we get that, that means in terms of similarity parameter, the partial differential equation can be boiled down into an ordinary differential equation. So, that is the beauty of similarity transformation. So, partial differential equation gets transformed and ordinary differential equation by using similarity transformation. ODE being easier to solve, so that helps us in our solution. So, people do the similarity transformation to simplify the mathematical tediousness of the problem. Okay. The similarity parameter is also known as a combined variable parameter, and it is a function of x, a combined form of x and y, and there are two thumb rules one has to remember whether a problem will be having a similarity solution or not. Two thumb rules, so that a problem has similarity solution. What are these thumb rules? Thumb rule number 1, PDE, partial differential equation, should be a parabolic partial differential equation. Second, one of the boundary condition must be at infinity. So, this is very important. One of the boundary conditions must be at infinity. Why this is required? The boundary condition is required to be in infinity, so that the velocity field or concentration velocity profile or concentration profile or temperature profile does not get distorted because of imposition of any other boundary condition at the edge of the boundary layer. So, let it get developed and it will die down or reach the prescribed value asymptotically. So, therefore, the self similarity of the profiles are maintained. Because of that, the one of the boundary condition needs to be at infinity. So, these two thumb rules has to be met in order to have a problem, in order to a problem has a similarity solution. That means, if these two conditions, if a problem admits a similarity solution, it must satisfy these two thumb rules, but if these two thumb rules are there, then a problem may have or may not have a similarity solution. So, it is a sufficient condition, but it is not a necessary condition. Anyway, now let us look into an actual problem. We will be taking up an example. The first example we will be talking about the Stokes first problem. So, in this problem there is a pool of stationary liquid and we keep a plate at time t is equal to 0 in the pool of stationary liquid. This is y axis, this is x axis. At time t is equal to 0, it starts moving in the positive x axis with a uniform velocity u naught. So, what happens? The fluid adjacent to the plate will be because of the no slip boundary condition, it will be experiencing a velocity u naught, and because of the viscous forces the velocity keeps on decreasing, and at a particular y will be having the velocity decreases down to value of 0. So, therefore, at this place, at this time, at this location, the velocity will be equal to 0, and we call this a sort of boundary layer, and therefore, we consider the velocity is 0 there, and the fluid element staying at this location does not experience the movement of the wall at y is equal to 0. So, therefore, this is y is equal to delta. Okay. So, let us solve the velocity profile as a function of y and T. Okay. Now, we have some assumptions. The assumptions are fluid is compressible, that means density is constant. Second, one dimensional flow. Since the velocity in the positive x direction, the velocity in the y direction does not exist. So, v, the y component velocity is 0. Third is z dimension too long. Therefore, w, the z component velocity becomes 0, and all the derivative with respect to w should vanish. Okay. So, therefore, under these assumptions, one can write down the equation of continuity, one can write down the equation of motion, can derive the expression of velocity expression as a function of y and t, and then once we formulate the governing equation, we will set up the boundary conditions and we will examine that whether this problem will admit a similarity solution or not. So, I stop it here in this class. I will take up this problem in the next class and completely solve this problem. Okay. So, we will be looking into the basically the application of similarity solution in actual chemical engineering problem. So, we will finish this problem in the next class. Thank you very much.